Hi children, today I am going to be discuss on chemical properties of P block elements, especially group 15 elements. In this session, I am including the oxidation states of group 15 elements and also the anomalous properties of nitrogen. Nitrogen, phosphorus, arsenic, antimony, bismuth are the members of this group 15. Of the periodic table. Among these group 15 elements, nitrogen it is having anomalous properties compared to the other members of the group. With the reason we can discuss in this video. Okay, first topic is oxidation state. In the case of group 15, when you consider the elements, nitrogen its atomic number is 7, 1s2, 2s2, 2p3 is the electronic configuration. So 5 is the valence electrons here. Oxidation state means you know that the positive or negative charge attached with the number. How the way the positive and negative charges it is occurring when the compounds, how the way it can accommodate the octet. On the base of that oxidation state we are mainly representing. Here every members of this group having 5 valence electron. So the way these members can attain the octet, either lose 5 electrons or gain 3 electrons. This is the easiest method. So which one is favorable? Either losing of 5 electron or gaining of 3 electron. Okay, losing of electrons we are expressing the positive. Gaining of electron it is indicated by -3. Which one it is easy? Losing of 5 or gaining of 3? Gaining of 3 it is more suitable compared to that of the losing of 5. So that's why this N and P it is existing as N-3 oxidation state and phosphorus also in the -3. Nitrogen it is readily forms -3 oxidation state, but phosphorus it is less readily it is forming the oxidation state -3. So by the receiving of 3 electrons these two members of this group attain the octet. Okay, then what about these 3? They are not readily accepting the 3 electron. They are existing. That's why they are not forming its -3 oxidation state. There is a reasons. Why? Because these members it is having lower electronegativity, because you studied that when the going down the group because of the size increases, what happens when the size increases? The attachment. Electronegativity means tendency to attract the electrons towards itself. It is not possible so easily because it is farther away. That's why there is no so much attraction between the nucleus and the last shell electrons. That's why electronegativity decreases. That is one of the reason. Because of lower electronegativity, they are not having the tendency to receive more electrons. That's one reason. And another reason is increased size, and another it is metallic character. You know that when we are going down the group, the metallic character increases. Because of these 3 reasons, these 3 members, that means arsenic, antimony, bismuth, they are not ready to form N3- oxidation state. But we told already nitrogen and phosphorus they are forming this 3- oxidation state because of the reason they are having smaller size and also higher nuclear charge. These are the 2 reasons for that. Then these 3 members, which oxidation state it is favorable? In the case of antimony and bismuth, they are tending to lose electrons instead of accepting. When there is a losing of electrons, you know that there is a plus charge for that oxidation state. So this antimony and bismuth, they are either 5 valence electrons there no. So for attaining the octet, 5 electrons wants to be lost. Sometime because of S2P3 configuration, some of the elements they are trying to lose this 3 electrons only. So when such a 3 electrons if it is losing, there is a chance of +5 oxidation state and also +3 oxidation state. Okay, in the case of antimony, they are forming both +5 and +3 oxidation state. But in the case of bismuth, they form +3 oxidation state but does not form +5 oxidation state. This +5 oxidation state, it is possible only in the case of covalent bonding. In the case of this bismuth. Okay. One example I will give you, BiF5. In that the bismuth it is existing as +5. Normally bismuth does not exist as +5 oxidation state, but when there is a covalent bonding, if it is possible, that situations only the bismuth it forms +5 oxidation state. So why this bismuth it is not interested to be as +5 oxidation state? Because as I told, S2P3 configuration for these members in this valence shell, they are losing only 3. So what happens? This S it is remaining as 2 electrons. That means it is paired one. That means 2 electrons. That is why we are saying that pair. So this S subshell, it is inert. Inert means they are not active in this losing. Yes, that's why it is said to be, this S subshell it is said to have inert pair effect. This inert pair effect, when any pair it is not active, it's not active in any cases, that it is said to be inert pair. So here in this, all the members there is an S2P3 configuration, because 3 electrons only when it is closing. That means this S it is having 2 electrons. That means these 2 electron, that means one pair of electrons it is inert. That's why we are saying that inert pair effect is the reason for this bismuth can exist as +3 oxidation state and not exist as +5 oxidation state. Reason, inert pair effect. So that's why we can tell that the nitrogen, the favorable bond -3, phosphorus -3, arsenic, antimony, bismuth, as we said earlier, it is +5 existing, at the same time +3 also. But you know that bismuth case, I told you, they are not at all interested to be act as a +5. +5 it is possible in the case of covalent bonding only. So we can conclude that when we go down the group, +5 oxidation state it is decreases. In the case of bismuth, you know that +3 only. Here in the case of antimony, +5 +3. Here +5 +3. That's why we can say that +5 oxidation state it is decreases down the group, but +3 oxidation state it is increasing. Reason, due to inert pair effect. In the case of oxidation state, some more oxidation state each element can exist. That means nitrogen exhibits the +1, +2, +3. -3 is the oxidation state we are preferring in all the cases. But +1, +2, +4, that oxidation states also it is possible for this nitrogen when it reacts with oxygen. Like that situation, sometime you can see that. I will show that example. Phosphorus also shows +1, +4 oxidation state in some oxo acids. Right? So examples are HNO3. HNO3. Here you studied that how the way the oxidation state writing in the last year you studied redox reactions chapter. So here -6, here +1. Okay, so here how much it will be there? +5. So nitrogen here exists as +5 oxidation state, and in the case of HNO2 here -2, here +1, so here +3. So nitrogen here you can see that +5 +3 oxidation state, and in the case of NO here -2, here +2. So nitrogen can exist as +2 oxidation state. And some other example, NO2 here -2, here +4. So from different examples you understood that the nitrogen can exist in different oxidation states. Clear? Then phosphorus also like that. Next one, we are discussing about the disproportionation of this group 15 elements. There is one rule. The rule is, in the case of nitrogen, if it is having the oxidation state in between +1 or +4, there is a chance of disproportionation. Disproportionation means this particular compound, this is an example of that disproportionation. This particular compound, it can undergo self-oxidation and self-reduction. That it is said to be disproportionation. So here, in the case of HNO2, I here written, this HNO2, when you check, you can see that the nitrogen is in the +3 oxidation state. We said early, the nitrogen, if it is having the oxidation state in between +1 and +4, that means this 3 it is included in that range. that particular compound can undergo the self-oxidation and self-reduction. That's the rule. That is occurring in acid medium, acid solution. So here you can see that the HNO2, it can disproportionate into HNO3 and H2O and 2NO. How the way the self-oxidation and self-reduction you can assign here. Here you can see that +3 oxidation state, it is changed to +5. So here it can undergo oxidation. HNO2, it is changed to HNO3. That means here oxidation occurs because of the increasing oxidation state. That you studied, when there is an increasing oxidation state, it is said to be oxidation. When there is a decrease in the oxidation state, it is said to be the reduction. In the next case, the nitrogen, here what happens? +3 oxidation state, it is changed to +2. That means this is reduction part. So here self-oxidation and self-reduction, it is occurring in the case of this HNO2. That's why it is said to be undergoes disproportionation in acid medium. In the case of phosphorus, nearly all the oxidation state disproportionate into -3 and +5 in both alkali and acid. Just like here itself. Here we said about that one rule, +1 and +4. In between that oxidation state only undergoes that disproportionation in acid solution. But in the case of phosphorus, nearly all the oxidation state undergoes disproportionation. Okay. Both in acid and alkali medium. And they changed into +5 and -3 oxidation state. And then the +2 oxidation states in the case of arsenic, antimony, bismuth, they become increasingly stable with respect to disproportionation. That means they are not ready at all for undergoing the disproportionation easily. So mainly the disproportionation, it is occurring for nitrogen and phosphorus. That is only about disproportionation. Now we can discuss on covalency. Covalency means the number of electron pairs which an atom shares with an adjacent atom. So how can we explain the covalency of this nitrogen? In the case of nitrogen, as you know, the 1s2, 2s2, 2p3 is the electronic configuration. This is the outermost electronic configuration. When you write the ground state electronic configuration of this nitrogen, you will get 2s and 2p like this. Yes, here there is no need of excited state, because you know that in the case of when we are considering this NH3 covalent bond formation, 3 hydrogens also involved in this bonding. So each hydrogen, you know that one is the atomic number, so 1s orbital only there. In 1s there is 1 electron in each. So likewise 3 hydrogens. So each hydrogen, it is making the bonding with this half-filled orbitals of this nitrogen and make a bonding. But this 2s also involved in that bonding. So how many electron pairs which is involved in this bonding, which is shared with the adjacent atom? You can see that 1, 2 and 3. This is also a part of this nitrogen atom. In this bonding, you can see that 1, 2, 3, 4. So that's why we are saying that the covalency of this nitrogen, it has 4. Because this is also a part of bonding. Then nitrogen's case we discussed in the case of covalency. But when we are going down the group in this group 15, nitrogen, phosphorus, arsenic, antimony, bismuth, in these situations when we are going down the group, you know that there is a vacant d orbitals. In the case of nitrogen, there is no d orbital, it is present. Because 2s2, 2p3 is the electronic configuration, there is no d orbital, it is there. But in the case of heavier members of the group 15, you can see that there is a vacant d orbitals in the outermost shell. So that d orbital, it will be used for bonding. So their covalency also will be expanding. So example PF6 minus. So the covalency, it will be extended. Now we can discuss on anomalous properties of nitrogen. Nitrogen, in the group 15 elements, nitrogen differs from the other members of that group in many respects. What's the reason for the difference between this nitrogen and other members of the group? There is different reasons. Due to the p-pi overlap, nitrogen forms multiple bond with itself and as well as with the carbon and oxygen. Here you can see that this is N2 and this is the single bond, other two are pi bond. So there is a chance of p-pi p pi multiple bond it is there in the case of nitrogen. And this Cn, this is that cyanide, there is a chance of triple bond. So nitrogen with, there is a formation of multiple bond with this carbon also. Here you can see that with oxygen there is a double bond. So one is the single bond, here other two are pi bond. So there is a chance of p pi bond it is possible in the case of nitrogen. Then tendency to form multiple bonds decreases as we go down the group. So elemental nitrogen exists as diatomic. As we go down the group means nitrogen, phosphorus, arsenic, antimony, bismuth. In this situation, when we go down the group, surely what happens? The tendency to form the multiple bonds, it is decreases. Then bond enthalpy of this nitrogen, that is another feature. It is very high, 941 kilojoule per mole. So for the breaking of that one, we have to be apply large amount of energy. So that's why nitrogen is almost non-reactive in its elemental form. Because of bond enthalpy it is very high, nitrogen that it is existing as a diatomic. Elemental form means an alone. So in the elemental form it is said to be non-reactive. Why? Because the N triple bond N, for that breaking needs large amount of energy, almost 947 kilojoule per mole it is needed. So when that much energy if it is there, then only the diatomic molecule of this nitrogen it is possible to convert it into the elemental form of nitrogen. So it is not so easy. That's why we are saying that this elemental form of nitrogen it is almost non-reactive. Okay, next to one, the phosphorus, arsenic and antimony does not form p pi bond, and that's why they are not existing as a diatomic molecule. Nitrogen, there is a chance of forming p pi bond, that's why it is existing as a diatomic molecule. But here there is no chance of p pi bond. But their valence shell wants to satisfy, no. So how the way the satisfaction it is possible? It is possible with the form of tetraatomic. So that's why they are forming tetrahedral molecules such as P4, AS4 and SB4. So here PP single bond, here you can see PP single bond, PP single bond, PP single bond. These are the phosphorus P4's structure. Compared to N triple bond N, there all the bonds it is almost considered as a strong. But here PP single bond it is considered as weak. Then triple and triple bond N. Because that we studied that single stick, double stick and triple stick. Which one it is easy to break? This one. That's why in the case of P4, that there is a single bond, single bond, single bond, single bond. It is possible here in the case of tetrahedral complex. So it is easy to break compared to that of the three sticks. Just like triple bond in and triple bond N. Okay. That's why PP single bond it is much weaker than that of the triple and triple bond. That's why phosphorus it is more reactive than oxygen. Because easy breaking it is possible. That's why P is existing in the elemental form, it is easy compared to that of N triple bond N. In the case of N triple bond N, there is no easy formation of elemental nitrogen it is possible. Why? Because bond dissociation enthalpy it is very high. On the contrary, phosphorus, arsenic and antimony, they form single bonds, but the bismuth, PI, it forms metallic bonds in the elemental state. So you understood that nitrogen it is existing as N triple bond N, but when you consider N single bond N, it is weaker than single PP bond. Why? Because there is one reason. In the case of nitrogen, when you consider there is a 5 lone pairs of electrons there. So when you consider 2, 4, 1, then nitrogen, so total 5. Another nitrogen 2, 4. So between this, we are considering only single bond. So how many non-bonding electrons here? You can assign here. So because of the presence of these non-bonding electron pairs, there is resulting smaller bond length, because they are resulting the interaction between them, repulsion, interelectronic repulsion it results. That's why they are come closer and it results the small bond length in the case of this N single bond N. And due to this, the catenation tendency, it is weaker for nitrogen. Why it is said to be the catenation? Catenation means self-linking capacity. That means nitrogen with nitrogen, carbon with carbon, oxygen with oxygen. That is said to be the catenation, self-linking capacity. So nitrogen single bond, that capacity it is weaker here. Why? Because of the fact that the interelectronic repulsion it is more. So that's why they are not interested to be as a single bond and single bond N. Catenation tendency also it is reduces. From the values you can understand that in the case of C single bond C353 is the bond enthalpy needed for breakage. But in the case of N single bond N, that is 164. That means easily we can break it. That means it is very weaker. In the case of P single bond P, you can see that 202. Arsenic 147. So from that you can understand that nitrogen single bond nitrogen, it is easy to break because the bond dissociation enthalpy it is weaker. Okay, lower bond dissociation enthalpy, that is the reason for the weakening of N single bond N. Yes, then nitrogen, as you know, there is a chance of forming p-pi bond only. There is no vacant d orbitals, or there is no d orbital. It is present in the case of nitrogen. But in the case of phosphorus, there is a chance of d orbital. So the phosphorus and other members of that family, they ready to form d-pi p-pi bond and does not form p-pi multiple bond. Okay, not only that, there is a chance of d-pi bond also. So the heavier members of the group, they are readily form d-pi and d-pi p-pi, and they are not readily form p-pi bond, and it forms only by nitrogen. Okay, then d-pi p-pi bond formation in the case of phosphorus, there is one example it is given. It is readily formed by phosphorus. So R3P double bond O, that means one is single bond, either is a other is a double bond. So phosphorus D and oxygen's P orbital, they are forming the pi bond formation. That's why this is an example for that. D-pi p-pi bond formation, it is possible here in the case of phosphorus. Two examples it is given here also. Then next one, the phosphorus arsenic can form d-pi bond also with transition metals. Here this is example for d-pi p-pi bond, d-pi p-pi bond, but here d-pi bond it is possible. D it is from P itself or other higher members, and this d-pi it is from the transition metals. Likewise d-pi bond also it is possible in the case of this phosphorus and other members of this group. The examples it is given: P C2H5 thrice and As C6H5 thrice act as a ligands. Okay, these examples also you note it down. And next one, the nitrogen it is not having the d orbitals in the valence shell. It has maximum of covalency 4 that I said early. The example also that it is NH4 positive. NH4 positive, the structure you know is that 1 1 1. This is H NH4 positive. This is the structure. So you can see that 4 bonds it is possible. So, and with the NH3 also I said about that. The covalency, maximum covalency it is 4. How? This is acting as 1 and 2, 3, 4. Likewise 4 is the covalency for this nitrogen. But in the case of heavier members of the group, as I said early, there is easy to expand because of d orbital it is there. So automatically their covalency it is extended. Heavier elements of this group, because of that extension, it is easy to form penta and hexa coordinated derivatives such as PCl5, ASF5 and PF6 minus. But in the case of nitrogen, there is no chance of d orbitals. That's why there is no expansion it is possible. So maximum covalency it is 4. That's why it does not form pentavalent compounds NCl5 and NF5. This is one important question: why nitrogen does not form this NCl5 and NF5 compounds? Because nitrogen does not having the d orbitals. That's why there is no expansion in its valence shell beyond 4. 4 means 4 is the covalence. I said that how it comes. So hence it does not form the pentavalent compounds such as NCl5 and NF5. Okay. So we can conclude that difference between this nitrogen and other members of the group. There is different reasons. First reason, Under ordinary conditions, the nitrogen it is existing as a gas, other elements are existing as a solid. Then as you discussed early, the nitrogen it is existing as a diatomic, other members it is existing as a tetraatomic. Then in the case of nitrogen it is having very little reactivity at room temperature, but other members of this group are quite reactive. Reactivity difference also will be there. Then nitrogen forms trihalides only, and it does not form, nitrogen does not form NCl5, NF5. Likewise, there is no chance of forming the pentahalides, but other members forms pentahalides. Then nitrogen it has a tendency to form p-pi multiple bonds. The heavier members of the group, they are having d orbitals, so they are having the tendency to form d-pi p-pi bond instead of the p-pi multiple bond. So that's another difference. And next one, the hydride of nitrogen, that means NH3 hydrides, shows hydrogen bonding. How the way hydrogen bonding? Yes, NH, then another NH. So this more electronegative nitrogen, and next ammonia's hydrides hydrogen, also between them there is a chance of hydrogen bonding. So hydrogen bonding facility it is therefore the nitrogen's hydride, but hydrides of the other elements does not having intermolecular hydrogen bonding. The next one, nitrogen does not form the complexes, but other members of this group there is a chance of complex formation. These are the main differences between the nitrogen and other members of that group. What's the reason for this anomalous behavior of this nitrogen? Mainly 4 reasons. Because nitrogen compared to the other members of the group, they are having the small size. You know that when it is going down the group, what happens? The size it will be increases. Yes, so one reason it is atomic radius, small atomic radius of the nitrogen, and next one high electronegativity and high ionization enthalpy. You know that electronegativity it will be decreases going down the group, ionization energy it is going down the group, it will be decreases. So nitrogen it is having high ionization enthalpy and high electronegativity. And next one, as I said early, the nitrogen it is having the tendency to form p-pi multiple bonds, and also nitrogen's electronic configuration, you know that 1s2, 2s2, 2p3. Here there is no chance of d orbitals. That's why there is no chance of p-pi bonding and all. So that absence of d orbitals in the valence shell of a nitrogen also causing the anomalous behavior of this nitrogen compared to the other members of that group.